Thank you, Thomas. Thank you, everyone, for being here instead of being at the beach. I heard it's really beautiful out there. My name is Igor Andreoni. I would like to tell you about how we are moving from ZTF, the Zwicky Transient Facility, into the era of new large surveys, such as Rubin Observatory and the Argus Array in particular. I believe many of you are familiar with ZTF. The Zwicky Transient Facility is a survey that started back in 2018 officially, has been producing a lot of products that the community has used to deliver science. And the mission for ZTF was to systematically explore the transient and variable sky. If we want to give a few ballpark figures, just to compare and contrast with your favorite surveys, ZTF is mounted on a 49-inch telescope, so 1 meter class, broadly speaking. It has about a 1 arcosecond per pixel resolution and can observe the sky in 3 colors, G, R, and I band. One of the major strengths of ZTF is its field of view. 47 square degrees, pretty good if you want to take repeated observations of the night sky. Let's do something different. We do questions now, and I am the one asking questions. So, regardless of where you stand politically, whether you're part of the ZTF collaboration, if you're a competitor of ZTF, if you don't care about ZTF, but if you are just enough familiar with it, what do you think are features or products that kind of help ZTF make us ready for the surveys to come? Products or features? Any ideas? Public alerts. Thank you, Thomas. Anything else? Brokers. So alerts that then connects to brokers and then connect to, well, give everyone the possibility to mine the data. And in fact, that's exactly what I chose to show for the slide. So the fact that the data are automatically and constantly processed in near real time. And that we have been doing that within ZTF for the last 8 years now has really brought the community little by little up to speed so that we're, I think, fairly ready for all the new surveys to come and the big data volume that we're going to explore. Now, we talk a lot about big data in astronomy. Let's remember, in optical astronomy, I'm pretty sure if you're an optical astronomer, you talk to your radio colleagues, they will tell you that the big data era started way long ago. We're amateur, but we're catching up as a community. Here is just, I would like to give a glimpse of what big data in optical astronomy would be like. Here is an image from ZTF. Doesn't matter how old it is. And it is a busy field. Now, I don't know exactly how many sources are out there. My guess, I don't know, tens of thousands. This is close to the galactic plane. Nevertheless, you can see also in that little square, close to the bottom left, you really see a lot of stars. Maybe there are some transients. You need image subtraction for transients and variables to really stand out. But this is not a full ZTF image. We said it's 47 square degrees. What you're observing is a quadrant. There are 64 of imaging looking like this one for each ZTF frame. Now, add some depth to it, the depth that you can collect with a new telescope such as Rubin for the LSST survey. The volume that you explore in every 30-second exposure is roughly 10 times larger. So that's why, even visually, you have a better feeling, I hope. This is why we need some big data techniques to go and mine your data. And the two facilities I would like to dive in a little bit more are Rubin, which I'm pretty sure is popular among all of you, and so many people from the more general non-astronomy community are so excited because the LSST has started only 1 week ago. And then I would like to tell you about the Argus Array. I think some are becoming familiar with it, but has been announced to the scene only a few months ago. Start from Rubin. It was conceived more than 20 years ago by Tony Tyson. And the mission for Rubin is to be synoptic. Do as much as you can with all the technology we have available, that we will have available in 20 years after the conception. And let's try to do all of that at the same time. Let's provide that legacy data set that can really feed everyone, from astrophysicists, cosmologists, solar system experts. And all the LSST goals revolve about 4 pillars: study of the Milky Way, of the transient sky, dark matter, dark energy, and there will be the most complete inventory of the solar system ever created. And here, once again, just a glimpse. You have a big mirror for Rubin LSST. That's good if you really want to go the distance, explore large volumes. It's a 6-meter class telescope. It is the largest camera ever built, certified by the Guinness World Record. It has 3.2 gigapixels for each frame. And something quite amazing about Rubin is that it can really span from almost the UV to almost the infrared, so from U band to Y band. So we'll have a very colorful, deep image of the universe. And the field of view, once again, is, it's not quite like ZTF, almost 50 square degrees, almost 10 square degrees, but more than enough to observe the sky in the time domain and do some of the science that we love. Just, I think, a fun source. I'm not here to tell you in detail about all the science cases that we are already exploring with LSST. I just asked my students, go find fast transients. And Anirudh came back with this source that is kind of fast, faster than a supernova. It's associated with a nearby galaxy. He was excited. I think it was a nova, so I got somewhat excited. But then you look at the distance of this transient. It's like 25 megaparsec. And this is going to be the norm. So even if the transient itself is maybe nothing groundbreaking, it's already telling us there will be a big story by the end of the 10-year survey. We'll find hundreds or thousands of sources that typically are confined to our nearby universe. Will be really observed at large distances, all the way to high redshift in the case of the most luminous transients. Switching gear to the Argus array. Rubin has just started, as some of us have already mentioned multiple times. The Argus array is being built now at the University of North Carolina, my home institution, and is expected to come online in between late 2027, early 2028. It's a very ambitious timeline, given that they started the actual building of the hardware for a bit more than a year ago. This is funded by Alex Gerko and primarily by the Eric and Wendy Schmidt Foundation. So this is private funding that go into ambitious, large astronomy projects. And the mission of Argus, the focus is the expression high speed. Everyone says that they want to take a movie of the sky. I found it in ZTF papers. I found it in LSST papers, obviously in Argus papers. But here, again, the focus is to have high-speed, continuous observations so that we can probe the transient sky in a rather new manner, especially if you want to go at depth comparable to what we can do we can achieve with ZTF nowadays. Argus will be a collection of more than 1,200 telescopes working together. It's not easy to operate, but they found a way. They will observe in 2 filters simultaneously. So some telescope will be equipped with G-band. Some other telescope will be equipped with a modified version of R band. And if you come up with a sum of all the pixels you have in all cameras, all together, they will reach 122 gigapixels per frame. And you may wonder, what's then the survey strategy? That's easy. You sit back, like you can lay on the beach looking for shooting stars. What you see with your eyes as you look up, that's more or less 8,000 square degrees of sky. That's the field of view that Argus will have instantaneously. And then think about it. If you stack all the images you acquire over a night as the Earth moves, you have more sky that is observed per night than 8,000 square degrees. You reached 21 to 23,000 square degrees of observations per night. I will not expand on the design. It's not, I think it's out of scope, but I thought this was a nice rendering of what the telescope will look like. And I showed that to my partner, and she knows about telescopes, but she says, these look gears to me, not telescopes. So I absolutely have to zoom in. The telescope will be made by 8 subsystems, subarrays, ratchets. There are various terms that are used to refer to them. These are huge. I've seen the bases that they're building for each of them. It's really it's impressive, like from here almost to the end of the room for each one of the subarrays. And that's where all the telescope will be mounted in a clever way such that you can even enclose the whole system in a warehouse and observe through a window. That sounds impossible and just nonsensical to do, but it's possible, and we'll keep the telescope clean, hopefully minimizing maintenance. And then I asked my postdoc, Jim, why don't we take realistic simulation of the Argus survey and throw in some gamma ray burst models? Since instead of showing a couple of plots, since many of you here are experts in gamma ray burst. Here, if you only consider the forward shock and the baseline 1 second cadence, this is what a typical gamma ray burst light curve will look like if you're observing just for an R band observation for 15 minutes. It's pretty beautiful sampling. I didn't quite mention the strategy in detail. The baseline for bright time, so about 1/4 of the month, is to observe the sky continuously every second. Thanks to Science CMOS technology, the readout time is almost 0. It's like 3 milliseconds. So you can do that. And for the gray time and dark lunation time, there will be 1 minute exposures. So on the left here, you see a plot of what you get adding maybe a reverse shock emission to forward shock for your favorite gamma ray burst, and how it can be sampled over half an hour in 2 bands. And in the middle plot, you see what you can get once the data are stacked in 15 minutes chunks. And stacking of data is within the scope of the project. You will receive alerts directly from the Argus team at multiple timescales. And on the right, you can see that you can detect gamma ray burst afterglows down to 22nd, actually more than that, more like 24th magnitude, days after the explosion. And interesting statistics is that we expect about 18% of gamma ray burst to be observable on the rise, so you don't even have to wait for peak to be able to get some light from them. And using realistic populations, Jim estimated that more than 100 gamma ray burst afterglow should be detected independently of gamma ray burst, regardless what is happening up beyond the atmosphere per year. So this is going to be one of the best gamma ray burst detector in the world, even without using gamma rays. And everyone likes to create phase spaces, parameter spaces, that make their survey stand out. So you can imagine who made this plot. Obviously, the PI of Argus. But I think it's actually quite explicative of the new capability that Argus will open. On the x-axis is the cadence you would have if you were to use your telescope to observe all the observable sky overhead. On the y-axis is the depth, just in magnitudes. So the higher you go, the deeper you go. You can find the Rubin standing out on the top right. So pretty slow cadence, but you can go very deep at observing the sky during the regular survey. Argus will sample a region of the parameter space quite unexplored at this scale. So going from a fraction, from seconds all the way to minutes. And like I mentioned before, stacking is within scope of the project. There are plans to co-add data acquired every 15 minutes, every hour, every night, and every week. And by doing that, we expect that every week, about 23,000 square degrees of sky will be imaged in 2 bands at a depth comparable or superior to what Rubin Observatory is going to achieve. I'm pretty sure many of you wonder, can I access the data? Well, for ZTF, there is a combination of private and public data. At the moment, it's 50-50. And then there are data releases that everyone can access from the IPAC and ERSA websites. For Rubin, all the alerts are going to be public. Anywhere in the world you're situated, whoever your PI is, you will be able to access information about transients and variables. For prompt data products, images, catalogs, and additional products, you need to be part of the US or Chilean communities or affiliated with a group that is providing in-kind contribution. You can ask me later if you're interested in learning more about all these aspects. All Argus data will be public. So alerts will be public, images will be public, with a caveat. They will not be able to store all the data. It's just too much. It will be tossed, largely. So people will be able to just access some data at native resolution, but at least the 15-minute stack should be accessible by everyone. This is very much still being determined together with Schmidt Sciences. I thought of finishing with just a few thoughts, if you bear with me. Some lesson learned and some food for thought, which, I don't know, if you're stuck in a very boring cocktail party, you can use a topic of discussion or maybe use this opportunity of this conference to maybe go a little bit more in depth and see what we can do about them. First lesson learned. We have already been living in a big data era for a pretty long time, even not considering gamma rays and radio. With ZTF, we already have to be geared up to tackle thousands and billions even of detections. What we're going to do with Rubin is just scale up. It's not an easy problem, it's a computational problem. Like Sri Kulkarni would say, it's about the, what did he say, the plumbing. But we know the science, we want to do well, and we're already in a good position for doing it. Something that I wonder is how the sociology will change, especially now that so much data is going to be public. Our collaboration is going to change. Our publication policy is going to change. I've heard good proposals, unrealistic proposals, and I'm just curious to see what's going to happen in the next few years. Second, something I learned sometimes at my own benefit, sometimes at my own expenses. Be very careful the size of the net you're casting. When you know what you're looking for, obviously you train your model to be perfect, well designed to find what you're after. And that's good. But everyone, especially I think the more senior people, will tell you, be ready for the unexpected. But the addition I would personally make is then chase it. It's not enough to just identify it. So provide resources to do follow-up, also what you don't expect. And hopefully, especially the TAC and various committees will be receptive about it. Food for thought. How can we, in the best way, integrate astrophysical fundamental knowledge with data science? I'm seeing quite a bit of a disjointment already. People who are way too much on one end, way too much on the other. Maybe I think it's way too much. Maybe you think it's fine. But this is a matter of discussion. For example, when your department is hiring faculty, should we have only AI expert or AI plus astro, or how can we best integrate to make the most of all the powerful tools we have available? Final lesson, final thought. I think ZTF really excelled in the science thanks to very complete spectroscopic samples. The idea was to have a survey that is photometric, but attached to it, there is at least one dedicated telescope for spectroscopy. We're not going to be able to do that in the era of Rubin, and probably not for Argus either. Are we really going to manage to make the jump in scientific knowledge that we plan with the limited spectroscopic resources we have available? I don't know. I'm curious to learn about that too. So I will leave you with just a quick summary, and also inviting you to think of new questions. I think that, you know, a lot of the pillars you saw, they were conceived 20 years ago, and that's great, and they're still very modern. But this is a really good time. Think of new questions and maybe integrate them with NASA flagship mission designs. So much is happening soon that we can use integrated in synergy with the upcoming big optical surveys. And I will stop there. Thank you.
Thank you, Igor. Do we have questions? Susanna, if we can pass.
Now, I have just a comment on your last question that for me, as you stress, spectroscopy is really fundamental. So here in Europe, we have a project that is called WST that is meant to do the survey of the sky spectroscopically with a new telescope of like 12-meter mirror. And that is the novelty of including the time domain science already in the science cases, and try to do AI, for example, on spectroscopic data to look for transient and so on, and there is target opportunity included. But this is is a proposition for the ESO expanding horizon, so it will be post-ELT, when the ELT will be working, let's say. I was wondering if there is something covering large sky survey spectroscopy from as a project from this US private foundation, if you know about some proposition in that sense.
First of all, I agree with your comment. I think that massively multiplex surveys really are the future for a lot of time domain science. Not all. They will always miss speed unless you sacrifice observing 5,000 galaxies, which is going to be hard to obtain. But
this is the new thing. In fact, they are in this project, they are really talking about a telescope TO for transients. So going in a region and put all the slits on, but also putting, like, since they have 40,000 fibers, they can use like 8,000, 8,000, 10,000 to look for part of the sky for transients, for example, for a follow-up.
Fantastic. And when it comes to other projects that are privately funded, as part of the Eric and Wendy Schmidt Observatory system, they have also funded 2 more telescopes that are relevant for spectroscopy. One is called LFAST, and it's essentially a concept similar to Argus in that you have a lot of small telescopes working in concert, co-adding all the data together, in this case to do spectroscopy, and the aperture should be equivalent to a 30-meter class telescope. It's going to be challenging to pull off, but they're trying. And the other facility that stands out nowadays is called Lazuli. It's a new space telescope that is being built, or is going to start to being built very soon. Its specs are not too far from JWST, but it is designed for transient follow-up. And in fact, the specs, the required features include being able to repoint the telescope within 4 hours, which I think will be transformational if you can do that every day, every night, for many transients with some data quality and range, not quite like JWST, but better that you can get in most cases with Hubble. So very much looking forward to that. Once again, ambitious timeline. They expect it to fly, I think, by 2029, but I should double check that.
Thank you, Igor. Any more questions? Well, I guess as a chair, I do have one. How do you how do you see sort of like these new large telescopes collaborating with other like minor, like let's say 1 meter telescopes? You're gonna have 23 magnitude stacks per day. So what do you use the 1 meters for now?
I think now it's a particularly interesting time for 1 meter class telescope observatories. For two main reasons. One is that, forget Argus, that is going to be in the northern hemisphere, even if the site is not fully disclosed, but it's going to be located in the continental US. And Argus will observe on multiple timescales, so we'll be able to observe also the bright transients. But Rubin will saturate at 17th Mach. And I'm pretty sure most of you are aware, a lot of the science is typically done on bright nearby sources. So bright sources, multiple colors, speed. That's another space that if you roboticize your 1 meter telescope, you can really have an edge over all these just incredibly powerful telescope, but that typically are just tricky to maneuver. So I see beautiful synergy between the large survey facility, the 1 meter class telescopes. I see science being done truly by working together, and the fact that so much of these data are going to be public should make this collaboration even easier.
Thank you for the hopeful answer. Any more? Mattia has a question.
Thanks for a nice talk, Igor, as always. So I have a quick curiosity, like for this Argus array. So you said there would be 2 filters, G and R. Like, is there a plan to, during the project, like add more filters, like redder filters, or?
So the current plan is to have an initial survey between 3 and 5 years with this setup. Behind the philosophy of the project is let's go as big as we can, as economically as we can, right? So you really want to minimize moving parts. You want to minimize maintenance. So here the idea, you will have 8 moving parts in the whole observatory. The 8 moving parts are essentially the basis of the subarrays. Everything else is screwed in, it's fixed. And if you ask any ZTF, they will tell you how much the mechanism that changes filter is when it comes to being faulty now and again. So for that reason, they plan to have fixed set of filters. And if you think about it, changing manually 1,200 telescope is not just an efficient operation. So my expectation personally is to conduct several years of a survey to filter, and then hopefully just go creative. Change filters, maybe change the exposure time, and maybe open new parameter spaces region for other parts of the electromagnetic spectrum.
Awesome. Thank you, Igor. Let's thank the speaker. Wonderful talk. Thank you. Our next speaker is Rahul. He's going to talk about TESS and ZTF discoveries. I also don't know how to do this, so. Okay, cool. So let's welcome Rahul, postdoc at Cornell. It's going to talk about ZTF and TESS stuff. Thank you.
Yes. All right. Hi, everyone. I'm Rahul. I am a postdoc at Cornell. I'm working with Anna Ho's group, and we've been using TESS and ZTF in conjunction to study both the early and the late time behavior of several different kinds of transients. So mic is working, right? You can all hear me? Okay, cool. All right. So to give a brief overview of what TESS is a transiting exoplanet survey satellite, but it's also very useful for transient science. And so the way TESS observes is that it has a 2300 square degree field of view and a 200-second imaging cadence across its entire field of view. It stares at a given region of the sky for roughly 27 days at a time, and then it shifts with the strategy of aiming to cover roughly 90% of the sky every 2 years. And so that means then that it will be able to revisit the same portions of the sky on timescales of 2 to 3 years. And so you can see here the mosaic of the entire sky from TESS observations of the first 7 years of its mission. So you can see that we've actually have pretty good sky coverage, and that's really helpful for 2 reasons. Basically, what TESS can help us do is we can probe the earliest moments of the transients given its continuous stare times for its observational sector. So if a transient goes off in that sector, we should be able to get early time test data for it. In addition, given that it revisits these fields after years at a time, we can then monitor these locations to see if the transient exhibits any sort of unique behavior. So I know we saw part of this plot in Igor's talk, but I just want to sort of extend it for TESS and show you how big of a field of view TESS has. And of course, with this large field of view, TESS is somewhat less sensitive than these ground-based surveys. However, as Igor pointed out, in the next few years, Argus will be coming online with thrice the field of view of TESS and a higher sensitivity. TESS's limiting magnitude right now is roughly 17th, 18th, so it's really good for the sort of brighter events. Argus will be able to go down to 19th and 20th, and probably even deeper with the stacks that Igor mentioned. So now I want to talk about some of the science that we've been doing with both TESS and ZTF. And to start off with, I want to talk about luminous fast blue optical transients, or LFBOTs. So these are luminous with absolute magnitudes peaking between -22 and 20. They're fast with the full width at half maximum being less than 5 days, and they're blue with their colors, G-R colors staying persistently negative. And so you can see here a light curve of 6 of the 15 or so LFBOTs that we know. And I don't want to give away too many of the punchlines because we have a whole dedicated session to this tomorrow, where we'll have some great talks about observations. But I did want to point out 2 key features of the LFBOT light curves. The first is that in the most luminous event that we saw, the LFBOT peaked at a magnitude of -22. And you can also see the rapid evolution, like from start to sort of, its decay, it's roughly 10 days. And then we're able to track it out to much later times through the use of like large telescopes, 6 meters, 8 meters, et cetera. And so the theory behind these transients is that basically there's a central engine that pushes a shock into a dense medium. But we don't really understand what happens in LFBOTs like hundreds to thousands of days after the event. So on the right, you can see here the X-ray light curve of 2018 CAL compared to X-ray light curves of other kinds of sort of fast transients. However, I'm not going to get too much into the progenitor debate in this talk. We have some talks about that tomorrow as well. And so what's really interesting about these LFBOTs is in 2022, AT2022 TSD was found to flare on timescales of minutes with luminosities that were comparable or like within a factor of 2 of the original transient itself. So this flaring phase occurred roughly tens of days after the initial event. These outbursts were red, suggesting a non-thermal origin, and they were quite luminous. And so what we thought would be interesting is whether we're able to actually search for these flares using TESS, given that it revisits these fields on timescales of months to years after the event, and also potentially search for any precursors. So you can actually see here, I might want to move this. Okay, maybe not. I don't know French, I'm sorry. Thank you. Okay, yes, thank you. So we can actually see that TESS has pretty good coverage across a variety of timescales after the initial transient, but in particular, we're interested in there we go. Yeah, we're interested in AT2024 QFM in particular because it was observed by TESS at the time scale at which 2022 TSD was found to flare. And I know in Zoe's poster, there's also hypercam follow-up data of this as well, but that lasts for a much shorter time than the 27-day TESS sector. And so you can see here an example of a TESS light curve for one of the LFBOTs. This didn't show any flaring, but what you can see here is basically we have the difference flux here in white, we have the background in blue, and we have the data that's been like sort of filtered to remove sort of bad times in yellow. And so one of the biggest systematics that we face in TESS is scattered light from Earth and moonshine like entering the camera. So that leads to these high backgrounds that you can see here, especially toward the end of each orbit. So we have to filter out this data. In addition, we get a lot of solar system objects passing through our aperture, especially for fields close to the ecliptic. And so those also sort of manifest themselves in these light curves. And so if we observe also any correlated light curve in background, the signal is likely not real. And so we constructed light curves at the location of each LF bot for all the times that TESS was observing them. And we found 7 things that could be flares. Unfortunately, they were all solar system objects passing through the aperture. And I'm not going to go into how we did this vetting during this talk, but I'm happy to answer any questions about that. So we don't find any evidence for LF bot flaring at like luminosities comparable to the original transient on timescales of hundreds to thousands of days after the event. And so there's 2 particularly interesting results. The first is 2024 QFM. We didn't find any flares that were comparable to the original transient, even though it was observed at the same timescale as 22 TSD. And then for the prototype event, AT 2018 CAL, which was observed roughly 2,000 days after the initial event by TESS, we didn't find any flares that were up to 1,000 times fainter than the initial event. So our results led us to 4 conclusions, and I've also included the QR code to the paper, if you're curious. The first is that we're able to constrain the duty cycle of this flaring to be less than 0.01 over a single test sector. We also find that given the non-detection of the flaring in events such as AT 2018 CAL, this flaring must decline in intensity or shut off at some point. That's one of the hypotheses. Alternatively, this flaring could be beamed with sort of weakly relativistic outflows. And so this might make sense because for 22 TSD, we might have been fortuitously oriented and looking, right down the jet that's launched by the central engine. But for the other ones, our viewing angles could be isotropically distributed like around the LF bot. And so given, what we saw in 22 TSD, what we're seeing here, we're trying to see if this is actually true in more accretion-powered transients, including TDEs. And so we're working on this project to search for flares in TDEs with a Cornell undergrad, Josh. He's working with us this summer, and he's making great progress. So hopefully we'll have some results in the next few months about that. And so looking forward to future surveys, right? So, what is the likelihood that, one of the other upcoming surveys on the horizon can catch this sort of flaring behavior? So with TESS, we're able to detect this flaring out to roughly 0.08 if it's identical to what we saw in 22 TSD. However, other upcoming surveys, such as LAST and the Argus array, could result in up to tens of detections per year of individual flares. But there is a big grain of salt, given that the rates of LF bots and the rates of LF bots that flare is highly uncertain. And you can see here what a TESS light curve of a flare similar to TSD would look like if it was situated at a redshift of 0.08. And here we have a sort of table that's in the paper about the estimated rates of how many individual flares we could detect with a variety of different surveys. And so you can see the most promising ones are likely going to be Ultrasat and Argus, but also maybe TESS if the LF bot is nearby enough. So with that, I want to shift gears a little bit and talk about what happens at early times in supernovae, which we're also able to probe with TESS. So in supernovae, as the shock is launched, it interacts with the circumstellar material and heats it up, and then this material re-radiates and cools. And so this transient is fast and blue, and so that means that it's also a huge source of confusion for us as we're searching for these LF bots. But they're interesting in their own right, and so we were like, we should take a look at these. And so because TESS is continuously observing, we're actually able to search for and constrain shock cooling emission in core collapse supernovae. So you can see here on the bottom an example of a shock cooling light curve in TESS with the early shock cooling peak, followed by the typical nickel peak. And the above is just a comparison supernova that was seen with Kepler. Another interesting one is 2023 AEW, which exhibited 2 peaks, the first of which was caught only by TESS, which is kind of cool. And this supernova was also interesting because it appeared to sort of change in type between the 2 peaks, from type 2b to type 1c. And so we were wondering, right, is there sort of a broader class of these sort of morphing supernovae? And in particular, we found that there is quite a large subsample of type 2b supernovae whose early time spectra during the shock cooling phase show very broad lines that lead to a misclassification as 1CBL. And then they're reclassified later on as the hydrogen shows up in the spectrum as a type 2b. So we're trying to figure out sort of how these events differ from normal type 2b supernovae. You can see here a spectroscopic time series for 2026 CHA, where we have an early black body spectrum, sort of like a blue ball, as some people call it, a typical shock cooling spectrum. We see here within a week that there's something that looks like a broad line. Studies of 2003 BG, a similar event, suggested that, these broad lines could arise from H-alpha blending with silicon-2. But if you've plugged this into your favorite supernova template matching code, it'll say a 1CBL is likely the likeliest explanation. And then after 2 to 3 weeks, we see persistently high H-alpha velocities of between 15 and 20,000 kilometers per second during the nickel-powered peak. And so this project is still in its early stages, and this is sort of a new area for me. So I'm really open to chatting about this or collaborating or just talking with the people at this conference this week. And with that, I will put up my conclusion slide, and I'm happy to take any questions. Thank you.
Thank you, Rahul. That was a great talk. Questions for Rahul? Igor has one.
I'm curious about this change of type. So I think over the last few years, there are probably many cases in which you have a spectrum of the shock cooling and then the main supernova.
Yes.
So is this a behavior you observed just in this one case, or is it something that you found in every case? Like, do you have any statistics? How often does this change happen?
Yeah, that's a good question. So this is not the only one in which we found this change. We found this change in like a fair few. I would say like between 5 and 10, but we're still working out the sample. And all this entire sample is sourced from all the ZTF-2Bs. So K. Ryan Hinz is working on a type 2B photometry paper. And so we're looking at all the early time spectra that we have of these 2Bs to see if there's any sort of change.
Thank you, Rahul. Any more questions? Susanna has one.
Sorry if I understood nothing. Maybe it's the case. I'm a bit puzzled by this misclassification, and so I worried. Do you have a look at if this can impact the association that we have with gamma ray burst? So usually with gamma ray burst, we have a supernovae that we thought are 1CBL. Yeah. Did anyone explore the possibility that we are misleading the thing, or it's impossible for some reasons?
That's a good question. So my understanding is that like we look where a GRB has occurred and we see a 1CBL, but we don't go the other way, right? And so sort of we're not necessarily, at least I don't think, there probably have been studies searching for 1CBL associated GRBs, but I guess we haven't looked for these 2B associated ones as well. Yeah, does that answer your question? It could be, yeah.
Hi, I'm back up here.
Oh, yeah.
Sorry, way in the back. Could you go back to your slide with all of the little rectangles? I think it was like slide 4. I forgot the number, I'm sorry. But the question is basically, you say that you're able to place limits on the duty cycle of these LF bots, but can you explain more about how you're able to do that since you don't have continuous coverage of these fields? And I think
this one?
Yes, thank you.
Yes. So the duty cycle is within one TESS observational sector. So that's like 5 days. Yeah.
Okay, sorry, I just missed that. And can you repeat what the it's 200 seconds for TESS?
200 seconds, yes.
Okay, great.
Yep.
Thank you.
Cool. And we have one last comment.
Yes, regarding this possibility of misclassification of 1CBL, I think perhaps in this case it's quite clear that the misclassification goes from 1CBL during the shock cooling phase to 2B during the radioactive peak. And GRB supernovae are always observed during the radioactive peak because before the afterglow is too bright. No, so. Okay, I see. Yeah. Okay, yes. For those online, Susanna was saying, okay, but when we look for one CBLs and try to constrain the fraction of those which should have a GRB associated, then we might be confused by this factor. Is it correct?
Cool. We have a
Okay.
wonderful discussion, but we have to move on.
Try to
Thank
get
you,
microphones
guys.
to speak because we have people online. So if you don't speak with microphone, they don't hear you.
Okay. Thank you, Rahul. Let's thank the speaker again. Let's welcome now Raoul. He's going to be talking about lens things and what we can do with them.
All right. Hello, everyone. So now I'm going to switch a bit topics now to see how we can use all these transients for something else, cosmology, with a strong focus on time delay cosmography, which I will introduce. And I will present all of that on behalf of the HOLISMOX collaboration. And we have also a good focus on supernovae. So as a reminder, if you already know, you're probably aware, but time delay cosmography works when you have a high redshift galaxy where something is variable, like a quasar or a supernova or a fast radio burst. And if you have a strong lensing effect with a formation of multiple images, then you will see a formation of multiple images with a time delay. And these systems are really interesting because they allow you to probe the time delay distance, which is expressed as the ratio of three distances, which is inversely proportional to h0. So it's really a one-shot measurement of a cosmological distance. These systems are really interesting because you only actually need the three ingredients to probe the time delay distance. You need first the time delays themselves between the supernovae or fast Fourier burst or anything, or the different images that you have. You basically need long monitoring of the system for that to measure what is the offset between the light curves. And then you also need the strong lens modeling, which is in orange here, which is a term that is allowing you to constrain the projected surface mass density of the lens, that is allowing you to reconstruct basically what is the mass distribution in the lens. And then you need this extra term, 3, which is the external convergence that will allow you to probe what is the perturbation from all the different galaxies and structures along the line of sight that will slightly change the time delays. So this technique has been now mature, I think, with quasars, and there is a nice prospect to extend now to lens supernovae, because these have a very high number of advantages compared to quasars. I think the main advantage is that supernovae, of course, have shorter variations, and they also fade away quickly in a few months to allow you to build a very refined model of the lens with all the information of the arcs without the supernova. But there are, of course, some challenges. First, the fact that you have microlensing perturbations from the stars in the lens that will produce a systematic in your time delay measurement, and also the fact that supernovae are, of course, rare, even more when they are strongly lensed. So here is the picture of strongly lensed supernovae that we had about 1 year ago. So it's not complete, but you see that most of the systems that were detected up to 2025 were cluster scale on the left, and they were also 2 galaxy scale lens supernovae on the right that had basically very short, about 1 day time delays between multiple images. And so these was clearly not enough to move the field to a time delay cosmography. And so these really show the need to select better and gold samples. And so these gold samples in the future will come mainly from Rubin, as we'll see in the next few slides, which is really going to be the key for this field. So there is one aspect that we can also tackle with lens supernovae, which is actually very relevant to your field, to this room, actually these systems, if you are lucky enough to detect them early from the first image on the left, then will allow you to predict the supernova image reappearance, as you see on the right, and trigger the observatories, especially in the optical, to get rest frame UV constraints on the very early phases of the supernovae. And this is really one of the only way for the community to access to these very, very early phases, at least until the next generation of UV space telescopes. So this is a field that we are trying to pursue now as well in parallel to time delay cosmography. As you see on the right, there is an example for 1A with 4 different progenitor models catched after 1 day after explosion, and you see clearly that really the diagnostic power is really on the UV. So these are really promising for that as well. So I would like to show quickly how are the prospects with Rubin. So we played the game to create MOX, MOX lens supernovae, focusing on type 1A for now, that we can expect to have in Rubin with all the range of follow-up observations that we hope to have at that time, to constrain the different quantities, which are the time delay distance that I showed you before, and also the angular diameter distance to the lens. And you see here that if you constrain all these 2 quantities and you combine 20 systems, you start to have very competitive measurements of H0. You see on the x-axis here, the constraining power is really on H0 with a slight constraints on omega m as well. But if you really focus on lambda CDM only, you will see that you get about 1% precision with only a sample of 20 lens supernovae 1As. So this is really promising, and so I will show next how we pursued the selection, how we started actually a few years ago. So of course LSCC was not there, and so we designed ways to select these systems. So first avenue to find lens supernovae is actually to just select strong lenses that are static, where you see beautiful arcs, and wait for a supernova to explode in the background galaxies. And so this technique has been actually shown to be efficient by combining the wide field of pan stars in the north with ZTF. Of course, the rates with ZTF were not so promising, between 0 to 1 per year. And we pursued still to see what we could get. And for 4 or 5 years, there was nothing more consistent with 0 than 1. Up to mid-2025, where finally we got a nice match in the ZTF public alerts to one of these pan-stars lens candidates, where the confirmation became obvious, as you see on the bottom right, with the detection of 4 multiple images with the Rubin Observatory. And as you see as well on the bottom left from CFHT, where you see you have 2 perturber galaxies, G1 and G2, that will produce this nice system, 4 multiple images, that have actually very high separation of above 1 arcsecond that are going to help us a lot to measure time delays. So there are not only 4 images, but actually 5, as you see in this different image, which is actually even more exciting for the analysis. So this is not only interesting because of its large image separation, but also because it's at high redshift, and that is actually a very rare supernova class. It's a superluminous supernova of type 1, with very high and very bright rest frame UV emission that you see on the right in the spectra we obtain in black, and very weak spectral lines. So that is actually very promising for anyone interested in superluminous supernova physics, where we can use these kind of systems for probing the rest frame UV. So these mark the starting point of the analysis of the system that is still ongoing in the Hollis-Mox collaboration, where we started with the first range of models to build the actual mass distribution of the system, especially of the mass in G1 and G2, where we got this LBT AO image with milli-arcsecond precision position of the 5 multiple images, with image E now being very bright and very safely detected. And we started with the first range of models that gave consistent results with 2 codes and a range of different image magnification from 1 to 10. This will pave the way for the final cosmography grade models that we will build in a few months. And the next step that is actually also ongoing is the measurement of time delays. For that, we have a collection of light curves from Colibri, LOT, Majdanek, Van der Stein, WFST, which is a lot. Thanks. And here, the challenge is really to make the most of these light curves and to have a safe blending of the light curves of the different supernova images, where we want actually to separate the static part of the system, which are the foreground lenses and also the host of the supernova, from the variable point sources of all the supernovae images. So here you see on the right, first version of the light curve, where we see that we are mostly getting the fall of the light curve. So how about the future or the present, I would say, because LSST now is starting, so we are entering in the new era for lens supernovae, where we'll now have many more systems to analyze. So the rates are actually even more promising than the 20 systems I showed in the introduction. There should be about 5 systems, 5 lens supernovae, 1 lens per year, even more if you consider also the type 2N and other types. And LSST will be extremely good for our discovery machine. It will be complemented with other telescopes on the ground to measure time delays and all the range of high-resolution imaging we need. But this is really promising, and the next question you want to address is how to move the selection process to this very high data regime in LSST. So how to do that? First, you can go back to the first approach, which was actually straightforward, and try to detect arcs, static lenses, and see if there is a supernova that would explode there. But the fact here is now that we have too many alerts, probably going to be appearing in the next few months, up to about 10 million alerts per night, which is going to be huge. And if we keep the same contamination rate in our selection, that will flow with thousands of candidates to inspect per night. So this is really not tractable. And so we made a lot of work here, as you see, to improve the neural network selection, to try to minimize this false positive rate. And we see that by combining networks into committees, we can move very much up left in this ROC curve and improve the selection a lot. So this was demonstrated then on real data from Subaru, which have a comparable resolution than LSST. And so this is going to be retrained and expanded to LSST. And this is complemented as well with this search of static strong lenses in the Euclid footprint, which is giving a lot of few 10K candidates in the next few years. So it's going to be going up to build a full catalog of static strong lenses in the Rubin footprint. Is it enough? I would say no, actually, because in many cases, even we think even it could be in half of the cases, we could detect the lens supernova with LSST, but without detecting the host. Why? Because the supernova would be too close to the critical lines with high magnification, but the host would not be. So we need actually another approach to be able to select directly these lens supernovae from the image time series, and this is the next step. This is what we are developing now, finding a way based on spatial-temporal networks to see the imprints of the multiple images appearing in the image time series. And so we have developed a new method that is based on a convolutional LSTM that will allow us to build an inference at each epoch. You see here, after the first epoch, you have only one observation in one band, and then you acquire more and more. And then you see that when you have more data coming in, the selection and the classification by the LSTM is going very much quickly up left, where after only ingesting 3 to 4 epochs, we now have a good selection. So this is really promising, and we think we are now ready to jump in with the tons of alerts that are going to flow in the next few months. How about in the last 1 minute, going even, I would not say further in the future, but aside, which kind of transients, apart from supernovae, could be useful in that respect for time-delay cosmography? And I think here the key is lens fast Rayleigh bursts, which are going to be very useful because now we are entering in the era of localized FRBs with chime and triggers, as we will hear a lot about during the week. So now chime and triggers are localizing 2 to 3 FRBs per day, and the rates are going to increase by an order of magnitude with CORD from 2028, where with CORD, you see on the right, the redshift distribution is going to extend a bit higher to the high redshift regime, and which is going to be enough for finding the first lens FRBs. And so this is an avenue that we are exploring now in Marseille with the FLAME project that is led by Daniele Michili, and that we are going to apply for the selection and for continuing these constraints on time-delay cosmography, taking advantage of the very high precision that we will be achieving with these millisecond duration bursts. Thank you. I will leave you with the conclusions and take questions if you have. Thank you.
Thank you, Rahul. I think we have time for one quick question. So I see Win. Maybe we can do two. Yeah. So just maybe first Win, and then you can go.
Well, thank you very much for this nice talk. So I was wondering, say 2025 WNY, do you think that it was a change if you were to reapply what now you've prepared in terms of deep learning algorithms and things to archival ZTF? Would you then recover more lens candidates and lens supernovae? Or is it that now we've gotten even better at our catalogs of strong lensing systems?
It's a good point. So with ZTF, we didn't have the option to really take advantage of the full time series because of the resolution that is in the ZTF survey, I would say. But then, yeah, I mean, as you say, one of the key aspects is now that we have more complete samples of static strong lenses on the sky. So that's going to be a good advantage for the future. And also, I think one of the other aspects is that now we know that because of the very, very bright UV emission of supernovae, we might not be lucky once, but more times. And so we should really include this class in the forecast. And so this class was never included. And so it could be that it will be also giving us more systems to follow up.
Thank you.
Cool. And last.
Yeah, just a quick question. What's the largest error source in the Hubble estimate from lens supernovae?
Sorry, I didn't get it.
Pardon? What's the largest error source? And if you increase the number of lens supernovae, you can really decrease error, or if something systematic from foreground lens system, it's
so are you talking about
systematic is still remaining.
Yeah, about systematics in this analysis, I would say that we, of course, with more systems, we will have more better control of systematics. And I think the key aspect here with lens supernovae is that we can break the massive degeneracy by waiting for the supernova to disappear and actually getting 2D kinematics of the lens, so the motions of stars in the lens to build a separate inference of the angular diameter distance to the lens, which is really a key here aspect to release this massive degeneracy and have a very robust inference. So here is, I think, the main improvement with lens supernovae. Yeah.
Awesome. Let's thank Raoul about for the talk. And the next speaker is Hugo. So I think it's over there. Okay, go ahead.
Yeah, so hi everyone. Thank you very much for having me. Also for giving me the opportunity to give a talk instead of a poster. Initially, I prefer the poster. So if you want a quick digest of this talk, you can also have a look at the online platform. So I am Hugo Tranin. I'm a postdoc at the University of Barcelona. And today I will present you this newly published catalog of galaxies in the nearby universe. So this will be for low redshift people, well, up to 0.4. And yes, it's especially optimized for transient astronomy. So let me start with the problem. Since 2017, we know that gravitational wave events can have an electromagnetic counterpart, but the error region of such events can be hundreds square degrees. So to narrow down the search for counterparts, we need usually a galaxy catalog. And the reference so far has been GLADE Plus, published in 2022. So yeah, as you can see for this image of the JW170817, the error region was quite large as well. But this is not limited to gravitational wave field, because the need for a complete galaxy catalog is only growing with LSST. So LSST will deliver millions of, has started to deliver already, apparently, millions of alerts per night. So to identify the nature of each transient and whether it's even extragalactic, you need to know what galaxy is the host. And also for the association to be reliable, you need the ellipse associated to each galaxy to represent its extent. So a point source catalog will systematically misclassify some transients as hostless. So here's the core problem. It's that, it doesn't show well, but anyway. No existing all-sky galaxy compilation satisfies the core key requirements. So to be an all-sky catalog, to have these ellipses representing galaxy extents, to have reliable distances, and to have also deep photometry. So for example, you can see that Siena Galaxy Atlas has an ellipse for a very nearby galaxy, so it has very nice extents in the footprint of the legacy surveys, but sometimes no distance, and so it's not all sky and limited to very large galaxies. On the other hand, GLADE Plus has only no extent information. So REGALADE at the bottom ticks all 4 boxes and is the first compilation to tick them all, basically. So to achieve this, we combined 14 input catalogs. They fall into 3 main categories, if you like: curated catalogs like NED, Hecate, the Siena Galaxy Atlas, some catalogs of having spectroscopic redshifts like the CDR1 and deep surveys. So pan-stars, the extended objects in the guide star catalog, Delve, and so on and so forth. So you can see the full list here. And so the result is REGALADE. So it stands for Revised Galaxy List for Advanced Detector Era. For non-French speaker, REGALADE also is the feeling that you have when you eat something very tasty and good. And it's an all-sky compilation with nearly 80 million galaxies, with ellipses, with distances up to 2,000 megaparsec, redshift 0.37. And it's also more pure and more complete than previous compilation, and I will try to show it now. So technically, how we did this compilation. So the cross match between catalog used this custom ellipse matching criteria. So 2 entries are considered to be one single galaxy if their centers are within 5 arcseconds, or if their centers are encompassed within the ellipse of each other. And this is the result. So on the left side, you see 3 different catalogs in the field close to UGC. I didn't put the name of the galaxy. Anyway, I can. It's on the poster. And on the right, you see the same field with which cleanly transforms into 1 entry per galaxy. So we also removed stars by cross-matching all these objects with Gaia. So actually, some galaxy catalogs are contaminated with some bogus, some stars as well. So yeah, well, you can see that using Gaia information, they are cleanly separated. So we use that information. notably using the Gaia color information. So for distances, we combined the different estimates. We chose the best one for each galaxy. For example, when there is a redshift independent or a photometric redshift spectroscopic redshift, sorry, available, we prefer this one. Otherwise, this plot shows that so photometric redshift or distance as a function of spectroscopic one, that averaging different independent estimates can lead you to better accuracy, actually. So if you have 3 photometric redshifts, you obtain a much more accurate distance in the end. At very low redshift, we still had some some ambiguous cases. So we had a campaign of manual vetting over 4,000, more than 4,000 objects. So 21 experts labeled them. So 27,000 classifications. So for example, this one is a bogus. This one is a nearby galaxy, distant galaxy, and 2 stars mistaken for a galaxy in one of the input catalogs. So at the end of the day, we select only the objects classified as nearby galaxies within this sample of ambiguous cases. So in terms of completeness, REGALADE significantly outperforms previous catalogs. So this figure shows the fraction of galaxies recovered as a function of distance. So this is estimated using the Schechter function. And GLADE plus, so you can see that GLADE plus completeness drops beyond, say, 500 megaparsec, especially the once clean out from its contaminants, while REGALADE, stay pretty complete out to 360 megaparsec. So yes, purity is the other side of the coin. The contamination fraction is still very high was very high at low redshift. So this was pre-cleaning contamination fraction. So we were able to remove more than 50% of the input catalog entries within 50 megaparsec to obtain a clean catalog of nearby galaxies and complete as well without sacrificing completeness. So yeah, the final points are the all sky coverage. You can see here the distance distribution, the sky distribution of galaxies within 100 megaparsec, where you can see the large scale structure, and also up to the distance limit of the catalog. And we have also uniform stellar masses and photometry over the full sky. And so next we tested on 3 science cases. How much time I have? Okay, right. So yes, 3 science cases. So gravitational wave follow-up, so target selection, ULX and HLX identification, and transient host recovery. So yeah, for example, this event detected in 2025. So we detected 80% more target hosts. Actually, this corresponds to better completeness in dwarf galaxies in REGALADE compared to GLADE. This is a most recent one. I can comment it later if you want. This so another science case we tested on was the identification of ultraluminous and hyperluminous X-ray sources. So in short, we're talking about X-ray sources detected by XMM Newton in the outskirts of nearby galaxies. And you can see that again. So these are interesting because they are either powered by intermediate mass black hole or manifesting a super Eddington accretion on stellar mass accretors. And yeah, in REGALADE we obtain we double the number of HLX detection, and maybe most relevant to transient people here. So in optical astronomy, we recover more hosts as well for faint transient discovered by the Black Gem telescope. So it's an array of deep telescopes located in La Silla. And for classified supernovae, so it's the brighter sample, we obtain a host for 90% of objects classified as supernovae on TNS. So let me focus for 1 minute on a science case most relevant to my team, which is luminous red novae. So they are intermediate luminosity optical transient produced by stellar mergers. They occupy a distinct region in the parameter space, in the absolute magnitude and timescale parameter space. So they lie between supernovae and novae. And so knowing the distance of the host is obviously very much needed to have these photometric candidates. So that's what we are doing now in a real-time pipeline. So we cross-match 95,000 galaxies at less than 100 megaparsec to the TNS every day. And we select alerts lying in this absolute magnitude range to find some interesting candidates for follow-up, because not everything falling on TNS is finally classified. So yeah, this pipeline is already running and has already flagged some events, some interesting candidates. So to finish with, let me show you the Rubin first light image with all the circled galaxies in the Virgo cluster. And so this one is the Euclid image of the Perseus cluster. So it's much closer to the galactic plane. So we don't have legacy surveys, but the catalog is still pretty good at detecting nearby galaxies. And perhaps most important is the data access to the catalog. So there's an online, here is my GitHub, and there's an online, there's a version 2 of the catalog. I've just published a preliminary version of it on my GitHub. And here is an online explorer where you can browse the nearby galaxies. Maybe if you want all the information, you can take a look at the poster or take a picture of this slide. The catalog is also available on Vizier, or you can also cross-match a list of coordinates to this catalog. Yeah, and this is, I guess I don't have time to present this, but this is everyday matching TNS to, matching TNS to REGALADE galaxies. So I will leave you with my summary. Yeah, thank you for your attention.
Thanks, Hugo. I think we have time for one question. One over there.
Thank you. You mentioned that this catalog is more complete than GLADE for dwarf galaxies. Can you give the bins of mass that you consider to compute your completeness, please? I mean, what is the lowest mass that you consider in your Schechter functions to?
So the lowest mass I consider, when I say completeness in dwarf galaxies, this is not related to the completeness curves I show here. Here is the completeness curve above, a tenth of the Milky Way luminosity. So this is the threshold I use for the Schechter function. And so it corresponds to pretty massive galaxies, like 10 to the 10 solar masses in stellar mass. And let me show my, I had it here. Here, yes. Here you see the histogram of the stellar mass for galaxies in the, selected for this gravitational wave event. So you see that the bulk of the distribution is in both GLADE and REGALADE. And the blue, the black histogram is only correspond to entries only present in REGALADE. So you can see here the range of the stellar mass. More or less galaxies less than 10 to the 9, 10 to the 8.5 solar mass in stellar mass are better covered thanks to the inclusion of legacy surveys mostly. Yeah.
Thank you. Just to be sure, if I can, sorry, you do provide the stellar mass in the catalog for each of the galaxy?
Yeah, absolutely.
And where does the information come from? What is the estimation?
It's a cross calibration of did I include this? It's computed from the deep photometry we provide for each galaxy in GRIs. So in this, you can see here the relation which is used, and it's also detailed on the paper. So you can see that we take as reference stellar mass published in this paper, which themselves take as reference stellar mass published in Cosmos. We are able to recover thanks to this relation. Accurate stellar masses whenever you have the ZRW1 magnitude. Yeah.
Awesome. Let's thank Hugo once again, and please the people listed in the flash talks, please come down. We have the second round of flash talks: Amit, Cristine, Koelln, Eddie, Massimiliano, and Nina. Awesome, great. Okay, so Amit is first. Okay, Amit, you can go ahead.
Thank you. I'm Amit Kashi from Ariel University. I'm going to talk about colliding wind binaries and supernova imposters. So what is a colliding wind binary? It's a system where you have two massive stars. This is the primary, this is the secondary. The primary is usually an LBV or a Wolf-Rayet star, and they have both winds, and the winds collide and create this conical shell. So this shell gets very hot and emits in the X-rays. But the problem is not so simple. You can see here that actually we usually have a lot of instabilities in the wind, and we also have to remember that this is a system that has an orbital motion, so we don't have a very nice symmetry. So this demands very expensive numerical simulations, and as you can see here, the secondary is here, and the primary wind approaches very close to it. In some cases, it can even reach it, and then we'll have accretion. Now, it's not a simple accretion, it's a more complicated accretion against stellar wind. So the wind from the primary tries to reach the secondary, but the secondary has its own wind that repels and fights against the inflow. This is how it looks in our simulation. This is a typical simulation. Here we zoom in around the secondary, and we see this shape where we have bubbles of secondary wind, and the primary wind flows along the vertices and tries to reach the secondary and get accreted. Now, this accretion also releases a lot of gravitational energy that later appears in supernova imposters. So we ran many of those simulations, and we came out with this plot. Here we have eta. What is eta? The wind momentum ratio, m.1v1 over m.2v2 over m.1v1. So and here we have m dot accreted, the amount of mass that's being accreted onto the secondary. We have three interesting regions here. This is a simple region with no accretion. So the secondary wind is too strong, so it repels the primary wind. This is the simple Bondi-Hoyle-Littleton accretion, but this is the new region with sub-Bondi-Hoyle-Littleton accretion. Basically, the gap between the accreted mass and the Bondi-Hoyle-Littleton line is created by the wind of the secondary. One last thing, those very strong events of accretion onto the secondary can create what we call supernova imposters. The LBV erupts and some of its mass is being accreted onto the secondary. It can be a repeating event because the systems are eccentric and it's more pronounced close to periastron passage. And this releases lots of energy that can create this supernova imposter. Thank you.
Awesome. You can click next slide, I guess. Well, it's a 2-minute flash talk, and to add adrenaline, I'll set a timer. So if you hear something, it's because your time is out.
Hi, everyone. I'm Tina. I'm a first-year PhD student at ESO in Garching, and I'm working together with Stéphane Blondin and Nando Patat to try and distinguish between different explosion models of type 1a supernovae. And we do that by looking at the stable nickel lines in the nebular time. So stable nickel has been suggested as a diagnostic for the progenitor mass because its production depends on the central density, on the core density of the exploding star. So in theory, if you have a more massive progenitor, then you have a higher central density and you have more stable nickel. And we look at nebular times because at this point, all of the radioactive nickel has already decayed, and we are left with only the contribution from the stable isotopes. So what we do is that we do use a 1D radiative transfer model called CMFGen to simulate what would happen to an explosion model if we fiddle with the stable nickel mass. And on the left, if you look, you have a spectrum of a violent merger model, and the color scale shows what happens to the lines, the strength of the lines when we change the nickel mass. So as you can probably expect, more nickel mass means stronger nickel lines. And on the right, you can see that there's a nice linear relationship between the total nickel luminosity at this time and the stable nickel mass. But also, if we extended this analysis to other explosion models, and you can see that while for each explosion model the linear relationship holds, there is a degeneracy between the explosion models and the stable nickel mass. So if you want to find out more, come find me or have a look at the poster. Thank you.
Great timing. Awesome. We might need help again with the slides, or maybe not. Okay, great. So 2 minutes.
Yeah, hi, I'm Carolina. I'm a PhD student with Norbert Langer in Bonn, and I'm going to talk about the impact of stellar mergers on the type 2 supernova. So this is models of binary stars. Why do we talk about binaries here? We know that the majority of massive stars will interact with a companion during their lifetime. And also we know that the current single star models do not always fit what we observe. And the kind of binary systems we're looking at, you can see on the left side in the box. So we have two main sequence stars in the beginning. One is more massive than the other, will evolve faster and leave the main sequence. Then we have Roche-Lobe overflow mass transfer and a common envelope evolution. If the common envelope cannot be ejected, we will have a merger. And eventually the star will explode in a supernova. In our population, we find that we have about 41% of type 2 supernova that come from these merger systems. We do the population synthesis with a rapid code called Combine, and then we identify which models will, which systems will merge, and then we take the whole secondary star and add it to the envelope of the primary star. And then we look at the properties of these stars because they will be different from single stars. And the first plot shows that we have enhanced envelope masses, of course, because we add mass to the envelope. Then the plot in the center shows you that we also have a broader distribution for a given core mass. A single star will have a given envelope mass, but these merger stars can have different envelope masses because we add different amounts of mass. And the last plot shows the enhancement of the helium in the envelope because the secondary also already has some helium that we add to the envelope, and also we completely mix the envelope. So if you want to look at that in more detail and talk about it, you can find me near my poster or anytime at the conference.
Hi, my name is Eddie Barron, and I invite you to look at my poster. It's very nice panchromatic SED of a very dim type 1a X supernova, 24 VJM, around 200 days. And it's very interesting because it makes both intermediate mass elements with both permitted and forbidden lines, and iron group elements, including stable nickel with permitted and forbidden lines, and it makes molecules, carbon monoxide, silicon monoxide. There's evidence for carbon dust. I can't prove it's pre-existing because I only have one epoch, but I'm pretty sure it is. And then the line profiles are actually quite interesting. You see the calcium doublet is resolved, so it's around 500 kilometers per second. The argon lines have velocities around 3,000 kilometers per second. And then the iron group elements have velocities around 1,000 kilometers per second. So depending on your biases, you can say that it's almost a completely mixed model or almost a completely radially stratified model. If you want to hear more about it, come talk to me. Thanks.
Awesome, thank you.
Perfect. Good afternoon, everyone. My name is Massimiliano Galeazzi from the University of Miami. You may notice that I'm a bit of an outlier at this conference. I'm actually here mostly to learn from you about transient science. It's a field I'm just getting into it. The reason I'm getting into it is from the more detector side. With my collaborators at Goddard, Boston University, and Johns Hopkins, we've been building X-ray telescopes for many years, including 2012, actually the first lobster eye telescope that was launched in space, showing that actually they will work. And now we know with Einstein Probe that they can work very well. Last one was actually last year. We sent a telescope for heliophysics on the surface of the moon. The reason here is we're getting more into the transient field, and we are actually working on a couple of projects that I'm presenting today. The one that I will focus is a proposal that we are submitting to NASA, a small explorer program in a couple of months. It's a sort of next generation transient instrument, combining a gamma ray instrument and a wide field X-ray instrument. The emission is called Extra, and the X-ray instrument is called MOXIE. So if you want to know what the next generation X-ray instrument may look like, or if you're interested to know what you will need for an instrument to meet the requirements of your preferred science, feel free to stop by or ask me. I'll be outside and I'll be happy to chat with you. Thank you.
Oh, okay, good. I'm Nina. I'm first year PhD in the University of Amsterdam, and I'm gonna talk shortly about pulsar scattering and also scattering of fast radio bursts. When the coherent emission from pulsars or FRBs get emitted, we don't get it right away because the emission gets scattered through because of the inhomogeneities in the ISM, interstellar medium, and we get delayed. Because of the multipath propagation, we get scattered pulse because some parts of the signal get delayed. And it's really cool to study that because we can learn more about ISM and different turbulent media. We've been working on a new approach expressing the intrinsic pulse profile using shapelets, which are Hermite polynomials combined with Gaussians, and it's really cool because it can recreate any physical profile shape. It has been successfully tested during my master thesis on pulsars using Southern Pulsar Array dataset. We got 250 pulsars, scattering parameters for 250 pulsars, 180 of which are new, and for some of them we have several epochs, and you can see that for some of them we can even see time variations of the scattering parameters. And now, as part of the CHIME collaboration, we've been trying to adapt this method for FRBs, which worked really well, and it can recreate the shapes of the fast rate of bursts much nicer sometimes compared to the previous method, for example, fit bursts. So it can be a nice addition, and it's also really flexible, and you can try different pulse broadening functions, and therefore study more about like host galaxies, environments, and intervening galaxies as well, and how they affected the scattering. That's all.
Awesome. Let's thank once again all the speakers. Amit,